Hi everyone, my name is Rafael Buescarpi and I will be the host of this presentation for this welove.fi campaign. So I hope you enjoy it and let's start. The presentation for today is called Secure Boot and Fault Injection, the Beauty and the Glitch. We will see why it's called with such a name because Secure Boot indeed will become the beauty and Fault Injection is all about glitches. The agenda of this presentation is the following. First, we will talk about secure boot. So we will actually see why is it useful and how does it work. Then we will talk about fault injection, the glitch in our story. In particular, we will see how does fault injection work. And then we will see how the beauty and the glitch work together. So how to glitch a secure boot implementation. We will see also a small demo example so that you understand how this can be used in practice. Finally, we will wrap this presentation with what can you do about it. Let's start. Let's talk about secure boot. So why is it useful? If you think of a booting system, for example, let's have a system that boots Linux in a modern system, or Windows or Mac OS. Basically, a modern system in general, if it does not have secure boot, it would typically boot as follows. First, we would start with some internal boot ROM. The chip would just start bootstrapping. Then this would load some code that would enable more memories, like disk storage or main memory. Then we would have a next stage bootloader and another next stage bootloader. And eventually we would start loading the operating system kernel, like the Linux kernel. In an ideal world, everything works fine. So let's say we have an embedded system and we have a Linux kernel. So how does a system typically boot if it's like this? So here you can see the different stages. For example, the first stage is going to be the boot ROM. After the system powers up, it will complete its power on reset routines, and then the boot ROM will start executing. This boot ROM typically will have the task of enabling some storage, like for example, this eMMC flash storage. Then it would load some code into some internal SRAM. Like in this case, we have, for example, uboot SPL. It's a tiny bootloader. And this bootloader, what it typically will do is enable a bit more main memory peripherals, a bit more peripherals. In this case, it would enable the DDR. And once we have this DDR enabled, then this uboot SPL will load the uboot bootloader, then it will execute this bootloader, then uboot would load the Linux kernel into main memory, then the Linux kernel would start, and then eventually we would have our full OS running. So this is most likely how the system that you're using for watching this video works, or something very similar. Instead of the Linux kernel, maybe it's a different operating system. But this is the ideal world. And unfortunately, in the real world, things sometimes go wrong. For example, you might accidentally run into some application that has been infected by ransomware, and this ransomware might decide, for example, to install itself in the same place as you would have this uboot SPL before, this second stage bootloader in this case. So what will the system do? Well, if you do not have a secure boot implementation, what happens is exactly the same. So the system bootstraps, then the first stage of bootloader will be the boot ROM. It starts enabling the eMMC storage, and then it will take this initial small code. Before it was uboot SPL, now it's our ransomware program, and it will start executing it. It will start executing the malware program. Then, unfortunately, this program does not start the system. This program, what it does is just encrypting all our storage. So we do not actually have a third stage bootloader. What we have is our data fully encrypted, and maybe this software starts asking for some ransom. So yeah, we are sad at this point. So this is something that secure boot can mitigate or nullify. What is secure boot? There are many approaches for secure boot definitions, but if we define it as what it is, it's the following. Secure boot is a design concept which ensures the integrity and optionally also the confidentiality of the loaded code in the bootloader chain. I will repeat, it's a design concept that ensures the integrity and optionally confidentiality of the loaded code in the bootloader chain. How does it work, this secure boot concept? In a nutshell, there are some elements that will be present in 99% of all the secure boot implementation. There are many flavors, many variations of implementing secure boot, but all of them have a lot of similarities. In particular, secure boot will always start from what is known as the hardware root of trust. We will have our hardware supporting secure boot with some internal ROM code, some initial code, that also supports some verification features. Typically, this is also accompanied by some key storage, like one-time programmable OTP memory or some eFuses. And this boot ROM, together with this key storage and fuses, what it will do is to ensure the integrity of the loaded firmware. So in particular, if you look at this scheme, the boot ROM will start loading the bootloader 1, this next stage bootloader, but before executing it, it will verify its digital signature. If the digital signature is fine, then it will run the code. If it's not fine, for example, if it was our previous malware application, it will refuse to boot it, and then our system still will not be encrypted. We can maybe restore this bootloader to an original one, and then we would be safe. If we take the previous example, how to boot Linux, we can see, for example, how to boot Linux with secure boot. In a secure boot implementation, we would have a boot ROM. This boot ROM typically would have some cryptographic keys. And then we would proceed to load next stage bootloader, then authenticate it, verify its integrity, and also, if the code can change, verify the authenticity of the code. So basically the integrity of the source. If it was encrypted, optionally, we will need to decrypt it. Then this first stage bootloader will also do the same with the next stage bootloader. We have here what is called a chain of trust. Every stage will verify the next stage. It will authenticate and optionally decrypt. Bootloader stages that you could have in an actual secure boot implementation for Linux. Well, most likely in your phone, you will have a trusted execution environment operating system. You might have U-boot in other systems. You might have the Linux kernel. So there are several boot stages. And something that also is very common is the moment you start jumping to the next bootloader stage, you also limit what is possible on the system. The next stage bootloaders have less privileges. So if your applications get compromised, they may be not able to, for example, overwrite the first stage bootloaders. So we have talked about beauty, about secure boot. It's a very elegant and simple design, but it's very powerful. This has saved many systems from a full system compromised because it can restore the code to a trusted scenario. Let's now talk about the other part of our story, about fault injection, about the glitch. So if we talk about glitching secure boot or glitching in general, how does fault injection work? Let's do a very small crash course on how glitching works. When you take a system and you take its datasheet, you would typically have an area which is the design safe operating area. The manufacturer knows how it works. The manufacturer designs the circuits to be stable in that area. But what happens if we go outside this area? Manufacturers typically will say this is disallowed or this is unknown. You should never use the chip in that area. But what happens actually if we go outside, for example, the voltage range? Let's see. If, for example, we go over the specified voltage range, like this 5.5 volts, and for a long time, typically what happens is that the chip catches fire. This is called overvolting and not very interesting as an attack. If, on the other hand, we decide to go very low with the voltage, below the specifications, usually the chip will not work, it will be sleeping. This other attack is called undervolting, and it's not a very interesting effect. However, there is a third case in which we can overvolt or undervolt for a tiny instant in time. This is called a glitch. We can have positive upwards glitches. We can also have negative downward glitches. Typically, we would try this second type of glitches, downwards, because it's less likely to damage a chip. And this is interesting because now it's very short. So the chip does not catch fire, does not go to sleep. So what happens? If we ask Google, then Google says, yeah, this is unexpected. So yeah, this is what Google says. Unexpected. But is it? Well, it's not true that everything is unexpected when doing glitching. If we start characterizing the voltage drop and the length, so basically the behavior of the system related to the shape of this glitch, if we have, for example, very shallow and very short glitches, so the voltage drop is next to zero and the length is next to 0 nanoseconds, then what happens is no change. This is just like noise. There is nothing happening to the power line, so the chip just works as usual. We could have, on the other hand, glitches which are extremely long and extremely negative. So if we are in the top left of this graph, that means we are dropping the voltage a lot, almost to 0 volts, and for a really long time. What happens there is also predictable, because then we would have a reset. The chip just thinks that the power is off, and after a while the power is up. So what happens if we go now to this area in between? So to this area in which it's not resetting, but it's not getting ignored, the glitch. Well, this is the area of the interesting changes. And then again, here magic happens because it's undefined. And here it's completely unpredictable. You can consider, for example, unicorns or magic. Really, it is impossible to a priori know what's going to happen. So, what is a glitch? A glitch is an event that will lead to this data or flow corruption. The effects of a glitch are basically unknown, and usually these glitches are caused by a physical hardware fault. Nowadays, there are some sophisticated attacks in which you can trigger these glitches only by software means in the hardware. If I think of glitching, I have to define it. For me, glitching is some sort of physical fuzzing. This technique of trying some physical signals and see if you can corrupt the software. So here, for example, you have this image of Super Mario Bros. 3. And these glitches happen, for example, when there was a bad contact between the cartridge and the console, that then the program was read incorrectly and corrupted. So this is also something that you can do by physical glitching with a voltage spike. But it's not only voltage spike. You can have laser glitches. You can have electromagnetic fault injection, voltage glitching, body bias injection. So there is a lot of ways of glitching. It's not just voltage glitching. You have seen in this short video how to do optical fault injections with a laser. So now we were talking about secure boot. So if we talk about glitching secure boot, what can we glitch? Let's go now a bit more in depth in how a secure boot process works. So here you can see in the bottom of this system graphic the power profile, and then you have the components of the system on a chip. And let's see what happens when we have a secure boot implementation. Step 1, you can see in the power profile the assigned area will happen in the hardware. So basically when you power up a chip, the first thing that happens is the hardware initialization. So the chip will first run its power on reset routines, so the digital hardware becomes stable. Then it will start copying the one-time programmable memory into some SRAM or special register. Then it will set up the clock system, stack pointers. So basically the hardware gets ready to start executing code. Next thing, the system on chip or the CPU or microcontroller unit, basically the computer part of your computer or your system, will start executing the boot ROM, and typically this boot ROM will initialize the flash storage. In our system diagram, we have this eMMC. You can see in the power profile that we have a bit higher power consumption because now we're executing code. And yeah, this is what happens in the second step. Third step, the boot ROM will instruct the flash storage to copy its contents of the second stage bootloader into the internal SRAM. So then here, because external storage usually uses quite some power, you can see in the power profile we have this big spike denoted with 3. And then we will copy the code. Now, the additional step that happens in a secure boot implementation is the following. Before we start executing the code in our SRAM, the boot ROM code, the secure bootloader, will verify the loaded code against the keys that are stored in the boot ROM or in the OTP. But basically, it will ensure that the code that we copied inside the system on chip is authentic and it has not been tampered. Then, as a last step, if the signature check, if this integrity check passed, Then we will jump to this SRAM code and we will continue the execution of the bootloader stages. But if something went wrong during this authenticity or integrity check, then we would fail. We would stop booting. The system will basically stop this boot chain, and then we would not execute this tampered code. These are the steps that you will find in any secure boot implementation. Basically, bootstrap of the hardware, then we will copy the next stage bootloader, verification, and jump to this code or not, depending on the success of this check. If we want to glitch a secure boot implementation, where to glitch? We have many operations. We have the hardware initialization, this storage initialization, the copy, verify, jump. So where do we glitch? As an amateur approach or a hobby approach, we can try what is called the blind approach. How do we try this? Well, if we ask a search engine, so now we ask Microsoft Bing, how do we do this? Then this is something that you would get. Yeah, oops, I don't care. So why? I don't care. A fault injection attacker, an amateur attacker, what in the end will try to break the secure boot implementation is to jump to this malicious code. So a malicious attacker, an amateur attacker will just start glitching in different areas. Maybe we don't even know at all what we are glitching, but we just keep glitching different places. And if we're lucky, then if, for example, with this last glitch, now we triggered this jump to my code in SRAM, then we're done. Of course, this is an approach that it might work in some embedded systems, but this is like playing the lottery or finding the needle in a huge haystack. The chances of succeeding in a modern system just by a bind approach of glitching, it's not that great, because bootloaders which implement secure boot strategies, they take quite some time to boot. So we have many times to inject this glitch. How to do this? Well, actually, glitching secure boot implementations with fault injection, this is a technique that has been done for many years. So there are some classical attacks that we are going to see now so that you can see how to do these attacks a bit more methodically, or how attackers attack secure boot implementations in a more directed way. One classical attack is to attack this secure boot setting. So the secure boot setting glitch, basically what it tries is to corrupt the data copy operation where we have this operation of, or this setting of the secure boot enabled or disabled. Most secure boot enabled platforms, they have some configuration option, and this configuration option can be enable secure boot or disable secure boot. Typically, this is one way irreversible. What if we could corrupt the system and trick it to make it think that secure boot was disabled? Well, this would be done by glitching, for example, early on, where this copy of the OTP might happen. And then if you trick the system to disable secure boot, then there is no more secure boot. You can't boot any code because there will not be a a bootloader verification. Step 4 will be not done in a non-secure boot setting. This is a classical attack, can be done. Another classical attack. This would happen in the step 4, in this verification of the code of the next stage bootloader. This classical attack is known as the hash comparison glitch or the signature check glitch. If you look at the snippet of the code that we have here, for example, we are calling this embed TLS library, but it could be any signature check library. Here, we are expecting some return value. This is C code. So if this thing returns, in this case, 0, then that will mean there is no error, and then we would jump to the else part. We would. If this embed TLS PK verify returns a non-zero value, then we do not boot. So what we're going to try is to glitch the moment that we are computing this comparison to see here, for example, if we can get this result to 0. If this code path, for example, we skip it, we corrupt it, something happens here. If we end up jumping here, then we're done. In our timeline, we would do this, which is at the very end, just before jumping to the code or failing. So we would start glitching here, and hopefully after a while, we would end up booting if we are an attacker. Another classical attack. This one is really old. This even was done in the early days of smart cards, for example, for satellite TV decoding. The infinite loop glitch. What do you do if this signature check fails in a secure boot implementation? So basically, if step 4, this verification of the copy of the bootloader in SRAM fails, how do you implement a failure state? Well, a classical one is to implement a failure state as an infinite loop. And here, if we look at this code, we might implement no boot as while one. What happens if somehow we corrupt this and then we end up skipping this instruction or this condition? So what happens if this while becomes 4, this one is 0, or we skip it? We end up here. And the beauty of this attack, or the glitch of this attack, is basically that now we have an infinite time. We can glitch anywhere because this is an infinite loop, so now we do not have any timing restriction. We can keep glitching, and as long as we manage to corrupt this while endless loop, we're done. We will end in our booting code. So this is a classical attack, and this is something that has been haunting many secure boot implementations. We might still see one of these things. Make sure that this you do not have in your implementation. Of course, it's not only about classical attacks, so there are more attacks, like for example, this combined attack memcopy. This is a combined fault injection and logical attack. In this case, how it works is as follows. All implementations will have to copy the bootloader from some non-volatile storage, like this AMC, to some volatile storage to execute it. Here, what we can do is to try to glitch these parameters of memcopy. What we will have is we will create, for example, this number to be bigger if we glitch it. And if we glitch, for example, this to a higher number, it might happen that our destination buffer, the base of memory that we're going to copy this amount of data, might not be able to fit all the data of this glitch operation. So if we, for example, instead of copying 1,000 bytes in hexadecimal, we copy 10,000, we might overflow this destination buffer. If we overflow a buffer, there is an attack, which is a buffer overflow, and we can overwrite the stack of this process. In particular, if we overflow this stack and then we overwrite the program counter in the stack, the moment that memcopy finishes, then we will return to whatever address we overwrote the PC with. The attack, what we have to do is we have to have a specially crafted EMSC content. So we have some payload, some shellcode typically known, and we will have some pointers to the start of this payload. Then we will try to glitch our system. In particular, we will trigger this glitching when we have this memcopy setting. So when we are loading the parameters memcopy, and we keep glitching. And if we manage to glitch this, and instead of, for example, 1,000 bytes, we have this bigger number, BAAD, then we might trigger this buffer overflow condition, overwrite the stack and the PC in the stack with some pointer that was stored in the EMMC contents. And when memcopy finishes, we will return to this pointer, which will be pointing to our payload that we also copied. So basically, we hijack the code execution when memcopy ends. This is a very powerful attack, and this works in platforms that use this kind of structures, memcopy. So as you can see, we can have now much more sophisticated attacks. But this is not all. There are many more FI attacks. So for secure boot attacks for FI, we have a lot. So we have seen the secure boot setting, the hash comparison, or the infinite loop glitch. But you can also, for example, unlock the debug interfaces such as JTAG by glitching. And then we don't care that much about secure boot. We might hijack the code execution flow directly by replacing the code in the CPU. We might have this combined memcopy attack. Sometimes you might have some platform-dependent architectures like controlling the program counter by glitching a value into it. Maybe we are transferring data and we glitch the instructions so that we copy into PC instead of memory. There are other attacks like the wild jungle jump. This attack, it's a bit more difficult and elaborate to explain. If you want to learn further, you can visit for sure this welove.fi page. Especially if you're a developer, at Riscure we're working on a new online course, which is Design Secure Bootloaders. There will be a software version which is released almost immediately. And there will be a follow-up for hardware. So how do you design bootloaders in a secure boot context, taking into account the glitches and fault injection? So I strongly advise you to check this out in the Riscure training website, which you can find also in the slide. Is www.riscure.com/training. Let's wrap up this presentation with a small demo example. So here, for example, in the Piñata board, this is a typical test target that we use at Riscure for training our customers on how to do fault injection techniques or how to harden a fault injection bootloader. So we have some secure boot code implementation. And in particular, this implementation is flawed on purpose so that our customers can see typical issues and then how to harden them. In this case, I just wanted to show you this infinite loop glitch on the Piñata board secure boot. And you can see in the bottom part the actual code of the bootloader. So you can see here we have a verified flash flag. And if this flag is 0, then we enter this endless loop. If it's not 0, then we jump to this memory address, which will be containing our next stage bootloader. So this is what we're going to try. We're going to try to glitch this infinite loop. And if we glitch this loop, then we would hopefully end up jumping into the code that we loaded. In here, we have these constraints of, I cannot show you now the actual setup because I'm recording this at home, but I built on my table this setup. So I took a picture so that you can see it. And here you can see the different parts of the system. Here I'm using a Riscure Spider. This is a fault injection tool, which allows to control very precisely our glitching parameters. This Spider tool is also connected to the Riscure glitch amplifier. This is the older model that I had available for this demo. Nowadays we have the glitch amplifier version 2, which is much more powerful and much more precise. And this is powering this system. But here, what I did is I loaded an invalid image for booting. So basically now I try to play as the attacker. This system has secure boot enabled. But as you can see in this screen that I also attached, when I have this illegal code, it's some payload that would print hack, but this is not digitally signed in a correct way. Then the system with secure boot says, yeah, this is illegal. Then I will print the message signature fail and the system crashes. How to do this glitch? Oh, I used Riscure tooling, I used inspector.fi Python, then I used the Spider tool and the glitch amplifier. This is how the new glitch amplifier looks. And I use glitching code, which is using something called a chronology glitcher object. Also, because there is an infinite loop, I don't need any trigger. And the code is very simple. So first I set the voltage of the Spider to 0 volts. Then I wait for a while so that I have a cold reset. The system is power off. Then I put the normal voltage, so the system is up. And then I glitch on the selected voltage port with a certain glitch voltage, a certain delay, and a certain duration of the glitch. If I also wanted to trigger my glitch, I could also enable this line to wait for a trigger. And then I start the glitcher. And then here I will also record if the glitcher times out. But basically after this, I'm going to try a lot of time, different configurations, different values for the glitch voltage, how much I drop the voltage line, also for different durations of the glitch, different lengths of the glitch, and also with different delays of the glitch. I will wait a lot. So for example, I can wait 500 milliseconds, half a second, to make sure that the signature fails and my system is stuck in this infinite loop. After a while, so this actually was something like 5 minutes, then I might manage to jump over this infinite loop. And as you can see, this is a picture when I managed to get this successful glitch. The signature fails, but it's not just this sad face. Then I also have here extra characters. Now I'm printing this hack payload, which is the code that should never run according to a secure boot implementation. Of course, this system is not a high-end security system. This is a training system, but this is something that illustrates this power of fault injection attacks. Here, just in 5 minutes, I had a secure boot implementation. I just tried glitching this infinite loop, which is not a proper practice if you have a secure boot implementation. And then I managed to hack it. So Takeaway notes to summarize this short presentation. What can you do? Secure boot is very powerful. So this is a beautiful design and it will help you a lot, but this will be true if it isn't broken. If you're an attacker, fault injection can attack secure boot implementations even with no software bugs. Because in some cases, we will be creating our own bugs, like this combined copy. We created our own buffer overflow. However, if you are looking at this presentation from the developer point of view, you should be aware that it is possible to harden secure boot code also against fault injection attacks. Finally, it is not easy to protect against fault injection attacks, but they can be mitigated and prevented. So if you use professional equipment and you follow professional training, you will fast track your security. And my advice is that you seek for professional advice from the experts. At Riscure, we have been doing fault injection analysis and evaluations for many years. We also manufacture high-end fault injection toolings that you can perform this testing. And we also provide software, hardware training so that you can also understand how fault injection works in the context of secure boot. Finally, here about security training, a slide. So we have many offers because I'm a principal trainer at Riscure. Then I would like to also introduce you to something, which is we also have online FI courses for developers, and we have a small demo which is for free. So you can also join in this website, and then you will be able to see our fault injection for software developers free course. You can join for free, and if you like it, then you can later purchase it. Of course, in Riscure security training, we also love FI. This concludes my presentation. I hope that you liked it. Thank you for your attention and have a good day.